Welcome to the next session. We have a great lineup of 3 speakers. And our first speaker is Professor Tongxin Li, who is a faculty member at the Chinese University of Hong Kong in Shenzhen. And Tongxin was at Caltech for many years. And then I also had the pleasure to work with Tongxin during my time at Caltech. And today he will talk about how to ML and also empower systems. Let's welcome. Thank you.
So I'm going to start with this, introduction of my kind of finding, because so I kind of figure out, right, there's a TV show, and so people there try to basically compete with each other and try to behave more like machines, right? So if you more like machines, you're better. So machines are somehow good if you try to train some AI, and they are kind of regarded as better if they basically ensemble or resemble human behaviors, right? So therefore, this actually causes a trouble if you really want to apply machine learning tools or some of the algorithm there. Try to for example, use large language model making some decision or action or advice. You try to apply them in your physical systems, for example, power system or other system, right? I think power systems is a pretty nice example because it's well established, and there are many classic methods. For example, if you're going to do some voltage control, you can either use droop control here, or there are some machine learning methods such as reinforcement learning or multi-agent reinforcement learning. And another example is for example, like scheduling the charging of EVs. So you can either use here the MPC. So when I was working with Steven, I think we tried to basically have done some experiments validating how much MPC is actually far away from the offline optimal solution. It turns out it's pretty good in the practical scenario. It's just 1 or 2% off from the offline optimal solution. So, but if you have more renewable energy, right, this is different because, for example, there is some policy change or solar generation, right? This will cause some variation of the environment. If you can really learn from the data, you can actually do better here. And the question is again, right? So how to make the methods more trustworthy? So the word trustworthy here is actually a pretty big term because people they always talk about trustworthy when there are many different aspects such as fairness, explainability, or privacy. But so in this short talk, I will just basically focus on especially the optimality and efficiency. Okay. So, and again, the question is basically how much should we actually trust the machine learning methods here? So we have done some work during my PhD, for example, for different small models, such as the linear quadratic control systems, or reinforcement learning, value-based reinforcement learning, and there are a bunch of different results here. And this is a typical example. Basically, I will show you, using the EV charging ACN data as a case study, right? So this is actually the real data from the Caltech EV charging facility. So you can see basically there are somehow like the, you show the number of charging sessions, the changing of number of charging sessions over time, and also the average energy demand over time. So you can see basically there is some fluctuations caused by different reasons. So first you can see a drop here roughly happened in November 2018 because the station kind of changed from free charging to paid charging. And later, because of COVID-19, right? So the stay-at-home order actually forces people to not working at Caltech. So you can see there's a huge drop here, and also you can see the pattern, arriving departure soldier time pattern in this in the real data. So this causes some trouble if you want to really learn scheduling based on this charging data. Well, on the other hand, if you think about MPC, right? MPC is the default algorithm running really in the facility. So you can see basically, there is a straight line there, right? So the purple line over there doesn't depend on the data, doesn't depend on how the environment changes. But if you can really learn from the data when it's pretty stationary, you can actually get better rewards. Okay, so the idea is to basically, learn how to trust the machine learning method, and there's a trade-off between how much you trust. So you can see different curves over there. So if you have more confidence on the machine learning methods, you can actually have lower, recovery when you really go, under this, out of distribution data. Okay, so this is one example, and this is another model we have been thinking about during my PhD with Steven and Adam. So this is a problem that you consider a linear quadratic control framework, and this is you can see you have the linear dynamics. Suppose it's stabilizable, and you have quadratic costs, and you have a control policy here, tries to output some action, and then update your state, and you have a machine learning agent basically trying to learn the perturbation in this model and send you a sequence of predictions. And this may not be the right perturbation because machine learning agent can make errors, right? So it's not always fully trustworthy. So we have developed some methods to handle this model, but today I'm going to talk about something new. Basically, this is a different models because in real-world applications, so what I learned from Steven is you always want to make your methods practical. So this is a more practical setting. Basically, you have a set of disentangled latent predictions. So later I will give you more examples why this is closely related to power system and a bunch of different applications. So now your dynamic system become somehow like your perturbation WT becomes a function of the independent components as. And so you have different time series corresponding to different components. Okay, so and then you can so the goal is to learn how much we should trust each independent components. And so here is a pretty informal comparison between the two models, the corresponding theoretical guarantees. On the left-hand side, this is for the original model, and you can see the compare ratio for the cost, for the quadratic cost, versus the optimal offline cost can be bounded from above by this term, this function. So what's interesting is the middle. So here is a function, a big O notation as a function of epsilon divided by omega of t plus epsilon. So what this tells you is basically epsilon is the prediction error. If the machine learning model makes more error, so by learning how to trust, you can still have a bounded compare ratio, right? Even epsilon becomes super large. And when epsilon is small, right, this term actually vanishes. But the drawback of this model is because it depends on the variability of W. If your fluctuation, your perturbation changes quite a lot when time goes on, this will cause somehow a high bound on your compare ratio. And on the other hand, so if you think about this different disentangled model, so you have also three terms. In the middle, you have a similar term that is a summation over all the independent components. And W here is a prediction time horizon. And there's no dependency on this variability thanks to a lemma that helps convert this model to a canonical online learning problem. Right? So this is a huge difference. I will not spend too much time on how to get this, but I will just showcase you basically a set of applications of this particular more practical model. And this is a problem relating to you want to control a draw under the challenge. So basically, you want to control a draw on a raining and windy day. You have two factors coming, basically try to push your draw away from the right trajectory. One is the rain intensity, have some rain dropping, and the other one is the wind speed, right? So by basically disentangling the two different forces, you can try to learn from them separately, and you have better, from the experiments, better compare ratio or the costs, right, compared to the original methods. So the yellow curve there is for a method corresponding to linear quadratic regulator, right? So it doesn't depend on the data. So even though your machine learning agent, goes from the untrusted version to the trustworthy version, doesn't matter, right? Because the classic control method is always there. And, but you can try to basically have different ways of combining the machine learning agents using different machine learning methods. So the blue line there is for the original model, I think. Yes, it's called self-tuning policy. Well, if you do this in this disentangled way, you can actually achieve even better trade-off. Okay? So, so the second application example is for a case study in power system. Well, in power system, you have multiple resources of fluctuations or generations at different nodes, right? Maybe one node is for, let's say, residential consumption of power. The other node corresponds to some solar integration to the grid, and another node corresponds to wind generation, right? They can be somehow disentangled, and they can be learned separately better, and you can learn how to trust them really well. And you can see, actually you have better trade-off compared to the original methods, and this figure corresponds to how you learn them separately. All right, so, and this is actually done on some real ISO data. Okay, so again, I'm going to spend the rest of my time talking about some new stuff, and this is a large language model, right? So I have spent time working on this. This is a work with my student, and so this is the background because people actually wonder, and this is a recent paper in March this year, I think. So people actually wonder how large language models actually can behave as in-context decision makers, right? So you try to basically have an environment, and then you interact with the environment through an LLM agent, right? Try to let the LLM make some decisions for you, and to see how it behaves. And this actually is for a case study of a multi-arm bandit problem with k equals 5 different arms, and so you can see it actually has different prompts. Design of prompts. So some of the prompts will give you some failure cases, and some of the prompts will give you some really successful cases. So it's pretty sensitive to different designs of prompts. And partially, maybe this is because LM is pretty sensitive to numerical rewards, right? And this causes some trouble. So what we do is we try to kind of turn to think about, right, what if you have some preference feedback, right? Rather than rewards, more like RLHF in the RL setting. If you have some preference feedback in the environment, can we actually learn from this? And can we actually, first test the capability of LM as an in-context decision maker in this scenario, removing all the numerical rewards and see how this works. Okay, and so this figure shows you basically a comparison, also in a case study of 5 arms. With classic algorithms for handling the dueling bandit problem. Well, also there are 2 different versions of benchmarks. One is strong regret, the other one is weak regret. Strong corresponds to basically you have 2 arms selected by the LM model, and so actually compute the summation of regret incurred by both the 2 arms. And weak regret only considers the minimum regret for the 2 arms, right? So this weak regret is actually a weaker benchmark compared to the strong version. So actually, the interesting thing is the LM model, the LM agents actually behave quite differently under the 2 different benchmarks. So for the first one, you can see there's a basically linear, so the regret is basically a linear function of the time regarding the LM. So the black curve is the best state-of-the-art LM API, which is the GPT-4 Turbo. And, but if you look at the weak regret rate, so you can see LM actually achieves pretty low regret throughout no matter, Yes, I will basically wrap up. The reason is, I will cut it off here. Sorry, yes. So the main reason is because LM doesn't converge, and there's some issues, even if you really force LM to converge. And so we have the design of a new algorithm tries to basically learn how to trust how much we can trust this LM agent, and they also have some theoretical guarantee. Well, so you can basically show, well, this actually performs pretty well even under some noisy and adversarial prompts, and it's guaranteed to converge even better than the classic baselines. So anyway, I will cut it off here, and so there are many future interesting directions around this, but what I feel most interesting is really to try to build a real system and see how the methods actually work and how in practice they can somehow help make our real problems even solved and try to make them more efficient. And this is what I learned from Steven. So finally, thank you so much for Steven's guidance through my PhD, and happy birthday. This is a photo from Chen and from you, so when we at the graduation day, and I really like this, so I put it here. Thanks.
We have time maybe for 2 quick questions.
Thank you, Tongxing, for the talk. I'm going to ask a question. I guess a couple of people, but I get different answer. Just want to hear your input. For the in-context learning, for the in-context learning, what is the reason the LLM, without getting exposed to those content was not in their training data, but somehow by doing this in-context conversation, they can somehow generate this answer?
So I guess first, it's hard to say if LM actually is trained based on the data or not, because the data, I think, so I have read some articles saying so this version is actually trained on 100T billion of the data, right? So you never know if the right data is actually in there. And so I guess because it's also a pretty fundamental problem, right? So it's never know if you really have some big model, the capability of the model can scale up based on the how many parameters in the model you have. So my opinion is, I think again, Steven said, right, all the models are not correct. So I will say again, so that's why we need to basically a method to decide whether to trust or not, and combine this with the classic methods, especially in power system, and try to take advantage of both. Thanks for the question.
Any other questions? A quick question? Yeah, yes.
So you mentioned that the approach is robust to adversarial prompts. What's the specific sense in which you tested that?
Oh yeah, thank you for the question. So I have more time to explain. So the noisy version of the prompts, basically you try to add some different wording or some noise in the prompts. I don't have the real prompt shown here, but for the adversarial case, basically you change the maximization to minimization. You tell the LLM to basically minimize reward rather than maximize reward, and this is definitely off the goal of what is the right goal is, but still you can guarantee robustness. Questions?
Okay, let's thank the speaker again.